again to our lecture discussion. So it's already the finals, and we are now entering Module 3. In Module 3, we have the title Set Theory. So this is not new to you. You have already encountered this when you were in your high school or even your senior high school. And under this module, we have two learning outcomes. First, illustrate the methods for defining sets and the properties of sets, and two, employ the Venn diagram in determining the cardinalities of sets. So I guess just reading the learning outcomes, you already have an idea of the things that we will be discussing in this section. So let's get into business. The first one, let's define. So a set is a class or simply a collection of well-defined objects. So when we say it's a collection of well-defined objects, we must be able to identify a common description or a common element that can now define the members, the objects involved in the set. And whenever we are considering sets, we usually represent a set using a capital letter, or we can represent sets by using capital letters. Then we also have, if an element or if an object is part of the set, we use this symbol and we read this as an element of. So if we have this symbol here, this is now read as the object X is an element of set A, or simply X is an element of A, or it means that your element X is part of class A or part of set A. And under our discussion on set theory, we have some basic sets that we will encounter along the way. So one, we have this symbol, capital letter R will now be for the set of real numbers, and then we have Z for the set of whole numbers or integers, and then we have Q can represent the set of rational numbers. So when we say rational numbers, these are the numbers that can be expressed as A over B or as fractions where A and B are integers, B not equal to 0. We also have the set of natural numbers. So natural numbers are our counting numbers. Okay. So those are some basic sets that we will encounter in our discussion. And another review, we have the way of describing our sets. A set can be described using the roster. In some discussions or in some books, roster method is also known as the listing method. So from the name itself, we just list down the elements. So let's say we have set A is the set containing. So by the way, when we write our set, again, we can represent it by capital letters, and then the elements of the set or the members of the set can be enclosed by curly braces. Then each element is separated by a comma. So let's say we would like to describe set A as the set containing the months of the year. Therefore, this will now be January, February, March, April, May, June, July, August until December. Okay, so that's the listing method. roster method. You just list down all the elements. The second type of describing the set is the rule method. So from the title itself, we create a rule to describe the set. So let's say we would like to describe the months of the year using the rule method. So instead of listing down all the elements, we can say that set A contains all x's such that x is a month of the year. Okay, so that's your set. So January is a month of the year, so x can have a value January. February is a month of the year, so x can be February. So as long as your element is a month of the year, then it can belong here. So what's the advantage of introducing the rule method? The rule method is very useful, especially when our set involves a very large number of elements. Because if we have a very large number of elements, then the roster method is very impractical. Imagine writing down all the elements. So let's say you have 10. So let's say you have, let A be the set of all students of St. Louis University. So just imagine listing down all the names of the students of St. Louis University. So that will be very tedious. While if you have the rule method, you can just say, let A be the set containing all x's such that x is a student of SLU. So you don't have to write down all the names of the students of St. Louis University. And then we have some axiom of sets. So actually this can be seen in your module also. So axiom of the universal set. So axiom of the universal set only tells us that every element is an element of a universal set. So let's say x is an element of A, set A. This implies that x must also be an element of a universal set. So when we say universal set, it is a set that contains all the smaller sets existing. So for example, if I say that the universal set is the set of students of St. Louis University, and then I say set A is the set of students in SAMSIS, okay? So the axiom of universal set is telling us that if you get any element in a given set, it must be an element also of the universal set. Okay, so if you are a student of SAMSIS, then it means you are a student of St. Louis University. Okay, and then uh, the next axiom that we have is the axiom of extension. And the axiom of extension is telling us when two sets are equal. But before we have uh, the axiom of extension, the axiom of extension tells us, oh, see, okay, so let's just define the axiom of extension. So the axiom of extension defines that set A is equal to set B, set A is equal to set B implies that for all x, okay, if x is an element of A, this must be if and only if x is also an element of B. So that's the formal definition when two sets are equal. If you get any element x X must be in A, and at the same time, X must be in B. So this is what we call the axiom of extension. And then, next definition is the subset. And the definition, set A is said to be a subset of B if every element of A is an element of B. And we use the symbol here, A is a subset of B. So if we will now take the definition of this, A being a subset of B means that for all X, if X is an element of A, this implies that X is an element of B as well. So what's the difference of the uh, axiom of extension? So for the axiom of extension, we say that two sets are equal for all X. X is an element of A. Look at this. If and only if X is also an element of B. So whenever X is in A, X must also be in B. But when we now look at the definition of a subset for all X, if X is in A, this must be in B also. But look at now the difference. So what's the difference? We now have an if-then statement. Okay? Earlier, uh, for the axiom extension, we have an if and only if. So here, if X is an element of A, this implies that X is an element of B. So basically, when we say that set A is a subset of B, all elements of A must be in B. Okay? Well, the two sets may be equal. We don't remove the fact that the two sets may be equal because there will be no violation there. If the two sets are equal, all elements of A are still in B. Okay? But here, it may also happen that set A is smaller compared to set B. And if we now remove the possibility that the two sets are equal, a more appropriate description of that is a proper subset. And for a proper subset, we now use the symbol A is a subset of B. So if we have a proper subset, all elements of A would still be in B, but we now remove the possibility that the two sets are equal. So when we have ordinary subsets, we still have the possibility that the two sets are equal. But if we have a proper subset, then A will definitely be smaller than set B. And then this theorem is in your handouts also. And the theorem states that let A be a set, then A is a subset of the universal set. Set A is a subset of the universal set. So if we would like to prove this, we would like to show that for all X, X is an element of A implies X is an element of the universal set. And by definition earlier, we have said that under universal class, for all X, X must be an element of the universal set U. So this must be true. Okay? And hence by trivial proof, which we have seen in the last section, the section on proving, then for all X, X is an element of A implies X is an element of U must be true. So if you want to go back to the definition of the trivial proof, just go back to your notes. Basically, yung trivial proof, ang sinasabi niya lang naman dun is, if you are given, if P then Q, if Q is true, regardless of the value of P, the statement is true. So here we have if P then Q. If Q is true, which is indeed true, then the statement will be true regardless if P is true or false. And then we also have the equality of set. So if we will now prove the theorem A is equal to set B. So if A is equal to set B, so how do we prove this? A equals B implies that for all x, x must be an element of A if and only if x is also an element of B. And where do we find this? This is actually from what we have mentioned earlier, the axiom of extension. Axiom of extension. And then, what's next? So we're using the definition now. Then from there, using the universal instantiation, so if we now choose an element y must be an element of A if and only if y is also an element of B. So this is by universal instantiation. Then, what else can we use here? Using now our definition of if and only if. Using the definition of if and only if, y is an element of A, if and only if A, what does that mean? That means that y is an element of A, then y is also an element of B, and y is an element of B implies y is an element of A. What rule do we have there? That's what we call by the rule of material equivalence, which we have discussed before, material equivalence. Then after that, what else can we have? So from that line, we can now use universal generalization. We have for all x is an element of A implies x is an element of B, and for all x is an element of B implies x is also an element of A. This is using universal generalization. Then from there, this means now that we have A is a subset of B and B is a subset of A, which now proves the statement. By the way, let me complete the theorem here. If A is equal to B, this means that A is a subset of B and B is a subset of A. So that's the definition of equality of sets. If A is equal to B, then A is a subset of B and B is a subset of A, which we have shown in this line here. And that now proves the theorem. Actually, this should be two-way direction from left to right, which we have already shown. And you must also show the right to left direction because this is an if and only if statement. This is just the first direction from left to right. I can make the right to left direction as your exercise. Okay, so I think I will just make the introduction on sets short so that at least the lecture video will not be very long. I'll just proceed with the next section on sets in our next video. Okay, so God bless everybody till our next video lecture.